757 Polymer Rheology, H. Winter, Lecture 8A. The capillary rheometer is built very simply. We started discussing that last time. Here I have a schematic drawing in front of me, and also I brought a few pieces. This is the main cylinder of a capillary rheometer. This is the piston, which is driven by some drive at controlled velocity. Now this capillary then is mounted to the die. Normally there's a metal-to-metal fit between the capillary and the die. It has to be nicely aligned, but then there's no leakage if you work with polymeric melts. If you work with solutions, you would put an O-ring or so in between. But for melts, it's just metal-to-metal contact. This is the die, and the die has holes in which we would mount then the pressure transducer. You see the transducer is pretty bulky. The capillary itself is very, very small, has a very small diameter. Maybe if I put it just in front of me, maybe if you magnify here, it's maybe a millimeter in diameter. It's a very small capillary, so the pressure drop is fairly high when the polymer is pushed through that system. And the membrane certainly is much too big to be mounted directly onto this capillary, so we connect the capillary with a small channel with a so-called pressure hole, and then there's a membrane up in front here on the transducer, and the pressure is transmitted to the back of this transducer and is measured with strain gauges. So that's the hardware involved in the capillary rheometry. Of course, there's a heating jacket put around, and the forces have to be accommodated with a large frame, but basically that's it. And for filling the capillary rheometer, you would pull the plunger, you would put in maybe a plug of material, you wait 5 or 10 minutes till the temperature is equilibrated, and then you start the extrusion experiment, and you go. Now the analysis of the experiment is very easy with respect to the stress, with respect to the shear stress tensor. We would measure the pressure gradient in the capillary, and this information would be transferred immediately using a momentum balance into the shear stress as a function of the radius, and you can see that there's a linear relation between the radius and the shear stress. We will use that in a moment, so keep that radial relation in mind. Now, the shear rate in the capillary is harder to determine. We get the volume flow rate from the speed of the plunger. You know, the cylinder is pushing down in the reservoir, and from the velocity and the cross-section area of that cylinder, you get the volume flow rate under steady-state conditions. And from that volume flow rate, we would like to determine the shear rate, and that's what I'm going to do next. We'll use two different methods. The first one is the method of Weissenberg and Rabinowitsch. So our objective is the determination of the shear rate. Measurement is volume flow rate. And the information available is really volume flow rate versus pressure gradient, or you could regroup this and say this is an average shear rate, velocity divided by the radius of the capillary. It's called the apparent shear rate, really, in the calculations often. And the pressure gradient is already presented as the shear stress at the wall. This would be this function which you just saw on the board for R equal capital R. Now, the analysis goes something like this. The volume flow rate is defined as the velocity integrated over the cross-section. So you have an area element of the cross-section, 2 pi r dr, integrated over the whole range. Now, this formula, and that's the only formula we are going to use in the moment, this formula can be integrated in parts. We can integrate this part, and we can differentiate that part and get a function. Here, this is the outside part where the velocity, and then this part integrated is pi r squared, is evaluated between 0 and r, and the velocity in the center is high, but the radius is 0 in the center. Now at the wall, the velocity is equal to 0, and the radius is high. So at both limits, this function is equal to 0, provided that we have no slip condition. So the no slip condition enters into the analysis. We have to keep this in mind. The remainder here is a function. Here this is the function we are looking for, the shear rate as a function of the radius multiplied with pi r squared dr and this integration. So nothing new, but now comes the trick. And the trick is the following. The radius is proportional to the shear stress. Remember the linear function I drew here on the blackboard. Remember here this the radius, as the radius increases, the shear stress increases. So we could use now the shear stress as the independent variable in our analysis instead of the radius, and would not change anything. So the radius is replaced by the shear stress. So wherever the radius turns out, here you have this. And the integration now goes from 0 to the maximum shear stress that's occurring at the wall. And with the normalization, the shear stress at the wall is out as a front factor. But now note that this integral, when you complete the integration, assume you know this function. When you complete the integration, then you get a function which just depends on the shear stress at the wall, and it's independent of the radius. So in other words, we can express the Q divided by pi r cubed as a function of the shear stress for experiments done on any radius. It doesn't matter, capillaries of various radii. And this is the curve which I was drawing here. Whatever rheometer you're using, you always get this type of normalized function. And that's the first result of this analysis. I will come back to this when looking at the non-slip conditions. Now, we can take the derivative of this function with respect to with respect to the wall shear stress. And let me draw this here for a moment. So we would have a function now where we have log Q divided by pi r cubed, and we have log shear stress at the wall, and we would have this function from our experiment. We would take one data point here, and we also would take the slope at one point. And this slope is going, that's what we are going to calculate. We will take the derivative and find that after all rearrangements, the shear rate at the wall itself is just a function of just Q over pi r cubed. Factor 4 is coming in, so it's basically this value here. And it is multiplied with a function which contains the gradient. So the result of that analysis is the shear rate at the wall, not the shear rate distribution. We only know the shear rate at one position, and that's at the wall. But since we know the shear stress at the wall, we can take the ratio of the two and then get the viscosity for the material element sitting at the wall. Now, we should not take this for granted. We are taking the property of an element, of a material element at the wall for characterizing bulk properties. But all experiments seem to confirm that condition, so we don't have to worry about it. So we only have the shear rate at the wall to analyze our experiment. Let's take the next approach for determining the shear rate, and that goes something like this. The flow in the capillary is sketched here. The shear rate for Newtonian liquid would increase linearly from the center to the wall. That's for Newtonian liquid, everything is linear. Velocity is a parabola, and the derivative of that is a linear function with a radius. So linear profile for Newtonian. And for non-Newtonian liquid, it's a function which goes in some nonlinear fashion, and we basically don't know what this function is. If we would know the viscosity of the material which we are going to determine, then we would be able to calculate that function. But note that in the center part of the capillary, the shear rate is lower for the shear thinning liquid, and near the wall, it's higher, and there's just one crossover point. So there's one radial position for which the shear rate is the same for Newtonian liquid and for our sample, for our shear thinning sample. We could calculate that position in terms of the linear analysis for the Newtonian liquid and in terms of a power law analysis, which requires a model. It's not precise, but with this model analysis, we would get the shear rate distribution, and we put those two equal to determine the radial position, kappa times r, for which both of those shear rates are equal. And kappa then is determined like this, and it's a function of the power law exponent in. Now, I plotted this function for various power law liquids, and you can see that, say, for capillary of circular cross-section, this this value, kappa, is about 0.8, pretty much independent of the power law exponent. So if you have a liquid, say, with a power law exponent between 0.6 or 0.7, you would not know it exactly, but you still would have a pretty good guess for kappa. And then you would use that kappa value and calculate the shear rate. Now, the shear rate at that radial position, kappa r, is given as the shear rate here from the Newtonian liquid. It's just the Newtonian solution times kappa r. And the shear stress is given by the linear relation. You know, you're at the position where you want to evaluate the shear stress, and you get that shear stress is just kappa times the shear stress at the wall. So now you have shear rate and shear stress for this material element at some intermediate position, kappa, and you take the ratio, and you obtain your result. You obtain the viscosity which you wanted to have. Now, there's still some error involved because you didn't know kappa in detail, but if you do this for your sample over a range of shear rates, you can plot your viscosity function now, determine your power law exponent. You get an improved value for n. You get an improved value for kappa, and then in your second iteration, you have a very good value already for your for the viscosity, for the shear rate, and then for the viscosity. So with this technique, you could immediately get viscosity data from a capillary flow experiment. You don't need the gradient dq, d tau. You don't need the experiments over a whole range. You take a point value for the shear stress and for the volume flow rate. You use this analysis, you immediately get your viscosity. So it's very, very simple. But surprisingly enough, none of the producers of capillary rheometers knows about this and uses it. So it's, I don't know, it seems to be too difficult. But I don't think this analysis is really too complicated. So next time you meet any of those, maybe you can inform them that they should analyze their data in a more simple fashion. This idea of the reduced shear rate came from Schimmer in Aachen. I should mention the author. So far, we just looked at the viscosity, the first material function in shear flow and steady shear flow. But we would like to know the first normal stress difference and the second normal stress difference. We would like to know those other two material functions of steady shear flow. And the question is, can we get those in capillary rheometry? And the answer is with difficulties. Let's look at a few examples where we introduce curvature in the flow. So far, we use capillaries which are round, of circular cross-section, or of slit cross-section, and determine the viscosity. But if we would use an annulus where the velocity distribution is somewhat asymmetric, so that the shear rate is different at the inner wall than at the outer wall, and of course that shear rate gives rise to normal stresses in that system, and the normal stresses are different at the inner wall and the outer wall because of that asymmetry in that flow field. So we can write the momentum balance for that type of flow and calculate the pressure difference between inside and outside, or the normal stress difference in radial direction on the inner wall and the outer wall, which is basically this here, and that's given by the second normal stress difference. This could be measured in an experiment, and it has been measured, but for the analysis of of this integral, you would need an estimate of the function. You would take a guess of the function for N2 as a function of shear rate. And then you would put your power law solution in for obtaining the shear rate, and then you would calculate this and obtain, as a result, N2 as a function of the shear rate. So it's not a pure experiment in the sense that you have to enter a model for the kinematics which will bias your result. Also, the normal stress differences are fairly low, and the pressures in the capillary are fairly high. So the experimental error will be significant in that experiment. It's very hard to get data from this. The shear rates could be very high when using capillary rheometers, and sometimes for the analysis of processing flows, we indeed would like to know the first normal stress difference or the elasticity in shear flows at very, very high rates. So that would be a candidate. A second flow geometry, which involves capillaries and curvature, would be a slit, which goes straight for a while so that the flow is fully established. And then we introduce some curvature and go back. Unfortunately, we cannot go because of the internal limitations, as you can see. So there's only a short distance where the flow can develop in curvature. The flow field, again, is symmetric. So we will have a contribution from the difference in gradient from the inside and the outside. But also, the streamlines are curved in this case. Now, the streamlines are under tension in an elastic liquid. And due to that tension, the streamlines would try to shorten it, will try to pile up on the inner cylinder. So there will be a higher pressure at the inner wall than at the outer wall, or the radial stress, radial normal stress, pi RR, at the inner wall is higher than the radial stress, normal stress on the outer wall. Is higher in pressure. And the difference, again, is given with the normal stress function. In this case, it's the first normal stress function because it's dominated by the tension in streamline direction. For the analysis, we again would have to convolute this integral, which is difficult, which would require the knowledge of the kinematics, and also would require an estimate of this function as this here as a function of the shear rate. The other possibilities where the tension can be measured, normal stresses in this liquid, in the polymeric liquid, appear not in a flow with straight streamlines, but as soon as we change the flow, if we go from this type of flow to some other flow, we would be able to measure we would able maybe to guess the normal stresses on the streamlines, and the integral over the normal stress across this integral of the normal stress over this area gives rise to total tension on the extradate. We could measure the tension on this extradate and then analyze the flow with a lot of assumptions. Basically, would have to assume something about the stress at the center line, and then we would come up with some information on the normal stresses. But it's a very biased analysis, I would say. Another approach which will give us information on the first normal stress difference is the so-called pressure hole error. When you have a slit, for instance, with a circular hole here and the pressure transducer sitting back somewhere as compared to a pressure transducer sitting flush mounted to the wall. Then in the vicinity of this transducer, the streamlines would be curved. And the tension along the streamlines would try to change this curvature, which comes in naturally, and try to straighten the streamline out, and basically will result in a lower pressure down here as compared to the flush-mounted transducer, which is exactly opposite. So when you come down the channel, you would say this pressure transducer should have the same reading as that transducer. But due to curvature and streamlines here, you have a reduced pressure, And the delta P then is a measure of the tension in the streamlines, and it's higher for elastic liquids than for less elastic. It would be 0 for Newtonian liquids. Into that system because there's an deceleration and acceleration involved. And for Newtonian liquids, the inertia effects are the only effects which give rise to different pressures, and this have been analyzed in detail. But for elastic liquids, low Reynolds number flow, the inertial effects are very small, and we indeed could obtain normal stresses, very nice normal stress functions with that setup. Arthur Lodge in Madison, Wisconsin, built an apparatus and is promoting that type of experiment to determine N1, and he got nice data. Another proposal goes like this. In a capillary of rectangular cross-section, you have different gradients in x direction than in y direction, and this asymmetry then in the analysis, together with the exit condition, if you look at the pulling at the extradate, can be reworked into some normal stress function, which is connected then with elasticity. But the it's very quiet about this experiment recently, so I don't know what the properties are, what the problems are in this type of experiment. Now I want to shift to a new problem or a new aspect of capillary rheometry, and that's viscous heating. Normally, capillary rheometry is used for very high shear rates, for measuring of material functions at very, very high shear rates. And the viscous dissipation is very high. The rate of this viscous dissipation is equal to the stress times the rate of deformation, instantaneous rate of deformation. So that's the local rate of heating per time and per unit volume. And that will change our experiment. We will not have isothermal conditions. So what can we do to maintain isothermal conditions or to keep viscous dissipation low? Here we simply put a thermocouple in little capillaries. You know, in capillary rheometry, one often uses very, very small dies here, mounts this onto the reservoir. Here you can see it's hollow in the back, so it's really a very, very short capillary. And in this capillary, we mounted thermocouples at the beginning and at the end for the bigger diameter. This is a 2 millimeter capillary, and just one thermocouple for the 0.5 millimeter diameter. Now, the temperature reading as a function of the shear rate, it goes as follows. With increasing shear rate, the temperature in the wall will go higher and higher. Note that the 2 millimeter capillary has much bigger temperature effects than the very small capillary. So the wall temperature is pretty much maintained in the capillary of small diameter. The same effect is seen in the extradate when you collect the extradate coming out of the capillary and measure the average temperature rise in this extradate as a function of shear rate. Then you have the highest rise for 2 millimeter capillaries as compared to 1 or 0.5 millimeter. So very little increase in temperature difference. So all of this indicates that we should go to smaller diameters. Here I have if you change the size for a moment, I've calculated temperature profiles which, here Becky, if you please change the size. Oh yeah, coming, good. So I assumed that the polymer enters the capillary at uniform temperature equal to the wall temperature, but then viscous dissipation will give rise to temperature increases. This is the center of the capillary. This is the wall of this capillary. So near the wall, the viscous dissipation is highest because shear stress and shear rates are high, and it's 0 in the center. Now, near the wall is also the isothermal wall condition, which gives rise to conduction. So near the wall, there will be as the temperature increases, there will be a gradient to the wall, and there will be a flux introduced into the wall. And that's really the this will cause difficulties for maintaining constant temperature conditions in this experiment. Now, for the 2 millimeter capillary or a 2 millimeter slit, I put both of them here, you see tremendous temperature increases. You have 6 degrees, not near the wall, but at some distance. And you can imagine that the viscosity measurement is faulty when doing that, because you have a lubricant layer produced during experiment, and you measure lower viscosities than you should when you don't analyze the temperature effect. Actually, it's very hard to analyze temperature effects, so we should try to eliminate them. We should try to keep the diameter very small, or the slit very, very, very thin, and then the temperature effects are very, very small. We can see that also by just looking at the equation of energy, by looking at the viscous dissipation term and the conduction term in that equation. So when comparing the two and taking the ratio, if this ratio is very large, the ratio is called the Name number, this ratio is very large, then the viscous heating effects are very, very large. I included already beta here as the temperature coefficient of the viscosity. This would be derived from a Arrhenius temperature dependence. If you remember the temperature shift factor of the viscosity, this is characteristic temperature difference derived from the Arrhenius equation. So if this Name number is large, then the capillary rheometry experiment is in problems. For our case, we would prescribe the shear rate. We would say you want to know the viscosity at 1,000 seconds to the -1. So that's normally prescribed. And with that shear rate and a power law model, we would be able to calculate the average velocity in the capillary, and we introduce this average velocity in the Name number and find that the Name number goes with R squared times some coefficient, which we cannot influence very much, is given by material properties, and the shear rate, which is prescribed, and the power law coefficient. So the bigger the radius, the bigger the Name number, and you saw that in the experiment. It's coming really right through this viscous heating effect. Another interesting phenomenon to discuss is slipping at the wall of the capillary. The shear stress distribution is not affected by slipping at the wall. We still would have the linear relation for the shear stress as calculated from the measured pressure gradient in the capillary. However, the shear rate at the wall is somehow hard to determine, because our measurement is not giving us the shear rate, it gives us the volume flow rate. And you see the volume flow rate has a slip contribution and a bulk contribution. And there's a deformation. The material doesn't move through this capillary like a plug. There's a finite shear stress at the wall, and due to that shear stress, there's a bulk deformation, which gives rise to some velocity gradients and gives rise to a contribution in this experiment. Now, if we rearrange, like we did before, the volume flow rate in terms of the integration by parts, same as we did for the Rabinowitsch relation, then the first part of this Rabinowitsch derivation doesn't disappear. This part is still there. This is the contribution to the velocity, to the volume flow rate from the slipping, and this is the contribution in the bulk deformation. The measurements of a material which slips go something like this. We took a silicone oil and measured its volume flow rate as a function of shear stress, and this is this green line here. For the unfilled material, regular behavior at any radius, we took about 4 or 5 different radii. It's one curve, and this is the result which we already analyzed together with the Rabinowitsch analysis. Now, if we add filler, put substantial amounts of filler in that system, we still have the same type of behavior at low rates, but then when exceeding a certain critical value for the shear stress, the curves depend on the radius. There's some slipping occurring, and this contribution then is radius dependence, and we see immediately that the slipping is changing our experiment. So here you have a simple procedure to find out whether your material slips or doesn't slip under the shear stress conditions which you are imposing in whatever experiment you're doing. It's a neat way of finding out the transition, the stick-slip transition of your specific material. It goes back to Mooney, who analyzed this data and then calculated the velocity, the slip velocity, as a function of the shear stress at the wall. So in summary, the capillary rheometers are very useful to measure at high shear rates. The experiments are limited to steady shear flow. We cannot do transients. Well, you could maybe pulse your pressure gradient and push liquid back and forth in the capillary and analyze that. But if you have a steady motion through the capillary, then you just get the steady state properties. The sample is enclosed in all conditions. Doesn't have a free surface, which is nice to when you work with polymer solutions or with degrading materials or have oxidation effects. It's a major advantage. You might lose that advantage when you fill your capillary rheometer with pellets and which have a lot of surface area. Then during the heating process, you still might get your degradation and all kinds of effect. But if we do it right, we have an enclosed sample and we will be pretty safe. Instabilities are interesting to study. We can use capillary rheometers to measure slip velocities and the onset of slip. And we can study the onset of melt fracture, which might have its origin in slipping, but it's more often it's a more complicated phenomenon. N1 and N2 under steady shear conditions can be measured, but that measurement would require special geometries to succeed. Additional information which we get automatically with capillary rheometer would be the extrudate swell. We could measure the geometry of the extrudate coming from the die. We could look at the extrudate from an annulus and also get swelling under those conditions. So that's a very common technique to get information beyond the viscometric functions. Also, the entrance correction for flow into the capillary. This is the pressure drop associated with this type of flow. From the reservoir, the liquid is pushed into the capillary, it's accelerated, and it's subjected to stretching in addition to the shearing. So that type of complicated deformation probes your material in a fashion which is very different from the steady shear flow. So it's worthwhile to determine that even if even if the flow is too complicated to determine specific material functions from that. But it's still very helpful information. The entrance pressure drop is, for instance, very different for linear polymers as compared to branch polymers for some unknown reasons. Maybe some reasons you will be finding out in your career sometime. So that's an unsolved problem. The experiment requires a large sample, which is no problem with commercial polymers, but it will bring you into trouble when you work with a chemist with some exotic new material. The capillary rheometry is just not the tool to work with this material. Let's break here for a moment and then move to rotational rheometers, to a different class of rheometers. Yes? Primary Rheology, HH Winter Lecture 8b. An important class of rheometers are the rotational rheometers. The principal geometries used are concentric cylinders, concentric discs, two discs just being placed opposite each other, and a cone and plate geometry. And one surface is rotating with respect to the others. Pressure is not imposed from the outside, so it's under ambient conditions. And we have to analyze those rheometers. The advantage of those rheometers is that the sample doesn't flow through the device, so we normally use very small samples. We can make the surfaces very, very large, so the stresses can be adjusted to the specific properties of the material, so we can measure rheology of very soft materials at very, very low stress levels. And then the most important advantage of the rotational rheometers is that we can measure in transient motion. We can impose all kinds of step strain, oscillatory shear, and see what's the transient response. And that transient response often is a very critical measure of the elasticity of the material. First geometry to analyze would be concentric cylinder geometry. We call those the Couette Rheometers. One cylinder is rotating versus the other. Let's say the outer cylinder in this case is rotating. The inner cylinder is attached to a torque transducer. There's a liquid between the two cylinders, and the torque transducer then measures the torque which is transmitted to that system. So one measurement is the torque. Second one is a pressure difference between inside and outside. That's very hard to do, but still, due to the curvature in that flow geometry and the liquid goes around, we have tension along the streamlines, and this tension then gives rise to pressure difference between inside and outside, and that can be analyzed in terms of the first normal stress difference in one material functions which we would like to know. We also measure the angular velocity. Angular velocity will be reduced into the shear rate, the torque into the shear stress, and the ratio of the two then it gives us the viscosity as a function of shear rate. Now the shear rate in this case, shear rate would be 2 times d r theta. If this would be 2 times d and on a radial surface in theta direction. This would be equal to the shear rate in our case. Now, due to the curvature of the flow, you cannot just take the velocity gradient. It's given as this group, and when you analyze this, when you differentiate this, it's a term which contains the velocity gradient and the solid state rotation. This is just a solid state. I plotted the velocity field down here. The velocity increases linearly from the center to the outside if we have solid state rotation. So if this inner cylinder is not existing, if you're just rotating the liquid. But due to the existence of the inner cylinder, which has kappa r as its radius, there is a zero velocity here, and the velocity goes from 0 to its full value. Now, the curvature has to be incorporated into the analysis of the experiment. The shear stress is related to the torque in this fashion. It goes with 1 over r squared. And again, it's not a linear function. The analysis of Couette experiments is somewhat difficult because of that nonlinearity. However, as you already guess, if the gap is very small, then the velocity profile is linearized, and you immediately get the shear rate from the rotational speed of the outer cylinder divided by the gap width. The shear stress is also linearized, so you can obtain your viscosity directly. In case of a wide gap, the flow is inhomogeneous, and you have to do some curvature correction. But if you want to measure the first normal stress difference, you need curvature. remember the stress on a material element in the Couette flow geometry is drawn something like this. It's like a piece here, and with this angular curvature effect. So the stress is different, has different direction on both sides, and that gives rise to tension in circumferential direction. But this tension is of no interest if you choose a gap which is very, very small, if your whole flow reduces to plane flow. So if you want to have N1, you need a wide gap, but then you have to deal with the inhomogeneity of the kinematics and correct for that. The kinematics is analyzed very nicely in Bird, Armstrong, and Hasaga, and in textbooks you'll find that. So I don't want to go into further detail. The next geometry, and the geometry which we use extensively for molten polymers, is the cone and plate geometry. A cone with its tip sitting at the center of this disk is enclosing a sample. Now, one of the surfaces has to rotate. We would measure the angular velocity, we would measure the torque, and we also would measure the normal force, the force pushing those two halves apart. Here I brought a typical setup. Here this is a cone, and you see the cone angle is very, very small. You hardly can see that. Maybe here when I tilt it, you see the mirroring. So the angle is about 0.1 degree in radians. Now the plate is touching, or it's very close to touching. The tip of that cone is taken away. So in a real experiment, you put this into contact, and then you separate it as much as is needed so that the virtual tip of this cone is just forming the perfect cone and plate geometry of that system. Note that your spacing is really fixed by that geometry. If your sample would shrink or expand to some volume changes, say with temperature or due to chemical reaction, you could not adjust the gap setting. This gap setting has to be always cone and plate, and if you introduce changes, you alter your experiment. Also, if you have now the normal stress effects due to the circular streamlines, these normal stress effects which tend to separate those two, in a rheometer which might be too soft, then you are operating under different geometry at different shear rates. And in no case you operate under the perfect cone and plate geometry. So you have to be very careful with the gap setting. And that's why those cone and plate rheometers are really built very stiff to maintain the geometry and the flow conditions for viscoelastic liquids. There are interesting transient artifacts. If you look at this very, very thin gap, and now you have elastic liquid, in this case, and start the flow, which would push this apart, and this pushing apart would require liquid to flow to the center to accommodate this new spacing. And that flow is very slow because you're talking about a very small gap setting. So there are all kinds of artifacts. About 20 years ago in rheology meetings, about half the meeting was covered with the discussion of those artifacts. And people didn't even talk about the material behavior itself. They just discussed possibilities of getting rid of those problems. Now, fortunately, those times are over. You still have to be very careful in your experiments. It doesn't mean that you couldn't run into those artifacts, but there are possibilities to master the experiment. And fortunately, we are studying material behavior now and not the artifacts in cone and plate geometries. Meissner was was a pioneer in really improving the conditions for those cone and plate rheometers. Now, in this case, let's talk about some more about the hardware. I brought some drawings. I think it's at the end of your handout. Here, this is a typical setup. The cone and plate is here in the center, and the the shaft here would connect one side with the motor and the other side with the transducer. And now comes the problem. The temperature in this region is very high for molten polymers, might be 200 or 300 degrees C, while this region down here is at low temperature, is maybe 50 degrees or 100 degrees C. So there's a large temperature gradient between your sample and the holder, and there always will be a flux. You cannot prevent a heat flux occurring in the system. You always have to supply heat near the sample to accommodate that flux down the shaft, and this is in the lower region and in the upper region in both cases. And we have to do something about that. On commercial instruments, hot air is being blown or hot gas is blown against the sample here in this vicinity, and that's okay. It supplies the heat, but the temperature field is fairly inhomogeneous. There also has been suggested to mount a heater in the plate, mount a heating element in the back part of the plate so that the sample would be heated by doing that. But remember that we still have to supply the heat flux. So you would have a heat flux coming out from the center of the sample, center of the disk, radially outward and down the shaft. So necessarily you have a radial temperature profile produced in your rheometer when doing that. We have a different proposal for this problem, and it seems to work very nicely. We put band heaters on the shaft on both sides, and with this band heaters we produce enough energy to supply the flux down the shaft. But we also control the temperature on both sides. The temperature here and there are equal, which means that there's no flux across here, and the sample is really guarded in an area of zero temperature gradient. And this gives us the isothermal temperature conditions which we need for our experiment. Here there are some more features later on when talking about blends. We will come back to this. We have an optical probe here. We measure fluorescence of the sample. There's basically the incoming light here changes the it's absorbed in the sample. It's changed to different wavelengths, and then its intensity and the fluorescent wavelength is being measured. And this way we can look at phase transitions. We can perform measurements on the angstrom level. So the cone and plate geometry is very advantageous for optical studies in addition to the rheometry studies. You can combine that very nicely. So that's a nice feature. Let me come back now to the cone and plate rheometer itself. We measure the speed of rotation of one of the surfaces divided by the angle of the cone, which is about 0.1 radians for most systems in that order, and we immediately get the shear rate. The shear rate is uniform throughout the sample. It's a homogeneous deformation. We can expose the sample to small and large strains. It's a very nice tool to have. The shear stress is proportional to the torque of the material, and again, it's available in the whole sample. What a luxury compared to capillary rheometry, where we only got the shear rates near the wall. Here we have the shear rate throughout the sample and the shear stress throughout the sample. The normal stress is giving rise to a separating force, a total force which is pushing the plate and the cylinder apart. And this force is being measured, and from that we measure the first normal stress difference at the imposed shear rate and get another interesting information. Now, this can happen under transient conditions or under steady state. So we might have time-dependent experiment, and all of this holds very nicely. So the advantages of this is advantages are the homogeneous strain, the explicit expression here of gamma dot tau and n. We can study transients. We can go to very large strains. We use a very small sample. Another advantage. That problems are with viscous heating. If we go to higher shear rates, Shear rates which would be quite normal or would be already low for capillary rheometer, maybe shear rates of 10 seconds to the minus 1, would be an upper limit for a rotational rheometer, would be a lower limit for capillary rheometers. Capillary rheometers would measure between maybe 10 and 5 or 10,000 second to the minus 1. And this goes from 10 to the minus 3 or 10 to the minus 4 up to 10 in shear rates. So they're really complementary in their range of shear rates also. At high rates, secondary flow will be induced, so the flow field is not the shear flow which we would like to have. Edge failure might occur, and the problem with the gap adjustment, if our sample changes density, we're kind of out of luck. Interesting is the analysis for the normal stress measurement in that system. It goes back to Weissenberg in the 30s. For that analysis, we will use a spherical coordinate system where the one direction is flow direction here. This is the phi coordinates. The velocity gradient for the shear flow is the theta direction, and 3 would be the radial direction of that geometry. And again, the angle is very, very small. And in our analysis, we would like to know now what's the normal stress in 2 direction. What's the normal stress on the plate due to the flow in that system? Remember, the shear rate is uniform, but still the normal stress might not be uniform throughout that. It might be a function of the radius. We take the R component of the momentum balance in that spherical coordinate system. R component is the 3 component in the shear flow coordinate system. And after neglecting inertia and gravity here, equation reduces to something like this. The term, this more complicated curvature affected term here, can be differentiated to have a gradient of the normal stress. We will combine this with this term here, combine it here to get pi RR. And we combine this here with those to get an expression of N1 and N2. Now, remember, N1 is a function of shear rate. And if the shear rate is uniform throughout the sample, then N1 is uniform. The same thing can be argued for N2. So this part here is constant throughout throughout the flow system. Before integrating here, let's rearrange somewhat. See, we are not interested in pi RR, in the normal stress in this direction. We are interested in pi theta theta. So we could now use N1, we could use N2 and saying this is pi theta theta, that's what we want, minus pi RR, that's what we got here. And this is constant throughout, so the derivative of this in radial direction is equal to 0. So you can see that the derivative of pi RR in radial direction is equal to the derivative of pi theta theta in radial direction. And you can just replace this term with pi theta theta, and you put it on the other side to get rid of the minus sign, and you have the equation for the normal stress which we wanted to calculate. Okay? So this is the procedure. We can integrate this now to obtain the distribution of the normal stress. It's actually linear in log R, so it's a linear stress distribution in this case. And note that the normal stress distribution, the normal stress which is a pressure transducer on the plate, if we have a transducer here, that's if we would say have holes here and measure the stress normal to that system. This distribution is calculated as a function of shear rate coming in with N1 and N2. It's given. It also depends on the normal stress at the rim, which can be expressed with the normal stress sideways and the second normal stress difference. So that's all set, and you can integrate now this here. You can put the normal stress into this term here to calculate the total thrust on the plate or on the cone. The thrust is given by the integral over the surface area here, the stress over the surface area. We have to subtract the atmospheric pressure because the atmospheric pressure came also in here with a free surface. So we have to subtract this, has to be a minus sign. And then some terms cancel. All the terms which contain N2 are canceling in here. And you will find that the force, separating force, is just given by the first normal stress difference at the shear rate at which we do our experiment, multiplied with a geometry factor. So it's a very nice, very straightforward analysis which helps us understanding the system. The artifacts, just to list them, talked about them a little bit, would be secondary flows, which are due to inertia and elasticity at high rates of deformation. Edge effects, the surface might not be spherical. There might be some lumps on that surface, and you will pick that up in your, especially in your normal stress measurements. If there are fluctuations over here, you will see fluctuations in N1. At large strains, when you put in maybe several rotations, this surface might not look as nice anymore, and then your data are falsified just by the presence of this free surface. In low viscous systems, the sample would not stay in here only if you have a bath of liquid, and that will change the free surface conditions and will give rise to some additional stresses. And then your cone might be in some angle, which I hope it isn't. It's you can check that. You have to align your rheometer, which there are some tools which you have to use to check whether you are not in that type of trouble. And then you have to set your zero so that the cone is touching the plate at every temperature level you're measuring, because the temperature gradients in the machine will give rise to various expansion effects, and you have to accommodate this in a conventional experiment. So the analysis is easy, but the experiment is somewhat harder. Now comes the third of our three geometries, and in this case the experiment is very easy, but the analysis is somewhat harder. So let's look at the parallel disk geometry. We have disks on both sides. The sample is of uniform thickness. You can just mold a sheet of material, stamp a little coin-shaped material from that, and there's some interesting optical effects also. Yes, it's ideal for optical studies. Yeah, have to use that pattern more often. It draws attention. It puts life in a static picture. Okay, so the sample is contained between the two plates. We measure the torque, we measure the angular displacement, and we measure the normal force and try to analyze that. Now, the shear rate is increasing with the radius linearly. There's a zero shear rate at the center, maximum shear rate at the outer edge. In our reference value would really be the shear rate at the outer edge given by the rotation at the outer end, the angular velocity times the radius, which would be the rotational velocity at the outer edge, divided by the setting, by the height of the sample. The shear stress is calculated using some type of Rabinowitsch relation. See, you're familiar with that type of derivation. You could do that yourself. It goes exactly the same way as Rabinowitsch did that. And the normal stress difference is gives us a mixed expression between N1 and N2, but the flow is not homogeneous. So N1 and N2 are a function of the radius in both cases, some unknown function. So this is the difference of N1 and N2 at the outer edge. And again, it will be a complicated evaluation, but it would be a possibility. Gives us a possibility of measuring the normal stress effects using F as an experimental value. So the advantages are the easy sample preparation, which is in some cases essential imagine you work with suspensions. You cannot push a cone into a suspension and then grind some particles maybe between them. So in this case, or you have a sample which has some interesting microstructure. You would not want to disturb this microstructure by pushing a cone into that system. So you can prepare your sample very carefully, and you can adjust your gap setting as your sample maybe shrinks or expands with temperature changes. It's the nicest treatment for your sample, let's put it this way, for your experiment. But the strain is inhomogeneous, and the other problems are the same as in cone and plate geometry. You might have viscous heating or this secondary flow or edge failure at high rates. So there you might not gain anything. In general, it's about the same. Now, let's apply that type of geometry to dynamic mechanical experiments. We would like to measure G prime and G double prime by deforming the sample periodically. Now, in our case, a periodic deformation would be introduced by oscillating one of the surfaces back and forth, and the amplitude at the outer edge would give us gamma r, and then we go from 0 to the maximum amplitude in that system, and that's what I wrote down here. Gamma goes from 0 to the maximum value, and the maximum value would be determined by its amplitude and sine omega t, and that would be prescribed by the motor of the instrument. And what would we want to know? We would like to know the stress response, but we measure the torque response. We measure not the stress itself, we measure the total torque which we get from integrating the stress over the surface. Now, the local torque is given as a local response to the local shear rate. Here, this is given by G prime times the sine function and G double prime times the cosine function. We discussed that when talking about material functions. This is the thing. Now, to get the torque, we have to integrate this, and here note that we have to get R times the stress times the surface area. So we have R squared coming in here. It's okay. So we integrate. We're putting in the shear stress, which I had before. We're putting in this local shear stress into this integral, and everything which is not depending on R is put outside already. So we only have this function of R here. And for the G double prime part, again, we have the same function of R. And if you evaluate this, you just get a geometry factor which you combine with pi up front. Actually, here I should not. Yeah, this 2 pi is already outside. Okay. So you put this geometry factor outside, you combine this with the front factor, and the result is quite interesting. The torque, which we calculate, the torque as a function of time, which is sinusoidal, or going at the same frequency as our strain, is equal to a geometry factor times the shear stress at the outer edge of our sample. So the nonlinearity doesn't cause any trouble, and this is due to the linear relation between stress and strain. All of this is only possible in linear viscoelasticity. And I will come back to linear viscoelasticity. So note that this experiment is okay for small deformations. The startup of that dynamic mechanical experiment is also interesting. We would like to probe our material on the time scale of a period, say, of our prescribed strain. Now here we modeled the startup of the stress as a response of the strain. And the stress really goes from 0 into some periodic function as a response of our prescribed strain. And we compare that startup of the stress to a calculated stress which would be found on a sample which was sheared oscillatory for a long, long time. So this sample would be in steady state, and you can see that the stress merges the quasi-steady state, and in about one period of that experiment. Now, in our calculations, we used a period in the order of a second and used a sample which had a relaxation time of an hour about. And you can see that the relaxation time of an hour doesn't disturb our experiments. We really can probe short times in that experiment if we choose low frequencies. And that's one reason why this experiment is so popular, is so powerful for analyzing data. In your handout, you have the equations which are used for calculating the startup. It's a straightforward exercise which you might want to go through. Okay, now let's measure another material function. Remember, we deformed the sample in a step strain experiment, something like this. The sample was sheared by some angle alpha, and we had a strain gamma 0 imposed on this material. And we wanted to measure the relaxation modulus as a function of time. And the person who produced very, very nice data of this, even for large shear strains, was Osaki and his group. And those are the data which we discussed already in connection with material functions. You have this data. And this is the relaxation modulus at small strain, and at large strain, somehow the modulus is reduced in value, and Osaki's result was the factorization of the relaxation modulus in a strain function and a time function. And we would like to measure that now. We would like to use the cone and plate rheometer to determine this modulus by imposing a deformation on the sample. We would put the sample here in between, and then we put a sudden rotation into the sample. We would deform the sample. We would input a strain into the material. It would still need a finite rise time, but this is in the order of a few milliseconds, maybe 100 milliseconds or so. So the sample would be deformed, and a stress would be introduced into the sample, and then the stress is relaxing as a function of time. Now, we could do that experiment in a cone and plate geometry where the strain is homogeneous and everything is easy to analyze, everything is fine. There's one experimental problem which we encountered here. When you want to have a large deformation, say maybe 25 or 50 shear units, a very large strain in that system, then the cone has to rotate by quite a bit by very large deformations to obtain that strain. And that will change the surface and will cause problems in your system. You could produce a large shear strain in the sample by changing the sample height. You know, you would you would introduce an angle theta. You would rotate your plate by some prescribed angle theta, and just do this. Yeah, you would do this with a thick sample, and you would obtain a small strain, or you would go to a very small, very thin sample, and you would get a very large shear deformation in your sample, but still your total angular displacement would be small, and the experiment would be okay. Also, if you work with suspensions and want to measure the stress-strain response, you would like to do this in a plate-and-plate geometry. And for that purpose, Sosky thought he should do the following. He should use the plate-and-plate geometry, and I want to discuss Sosky's correction, which is really the equivalent to the Rabinowitsch correction, but this is now for step strain. He imposes a step strain on the sample, and this is the value of the strain at the outer edge multiplied with small r over r, so this is the linear increase of the strain for our inhomogeneous experiment. The resulting stress is given by the integral of the shear stress, and this integral with the radius contains the radius here, and the radius can be replaced with the shear strain which we are imposing into that system. So we replace the radial dependence, and we just get the modulus as a function of strain, and you do the same type of integration as Rabinowitsch did, and you find now that the real modulus at some large strain is given by this front factor modified with this radius. Now the front factor is all you get if you work with a Newtonian material, with inelastic material. If you work in the linear viscoelastic limit, you only get the front factor. So you get this here, and we would call this the apparent relaxation modulus. You can rearrange all those equations, and you find now, this was Sosky's result. He finds the relaxation modulus. That's what you saw in Osaki's plot. Given as the apparent modulus, that's what the rheometer gives you as a result. You know, from the torque, the rheometer normalizes everything with the geometry, and it gives you the apparent modulus. And you measure that at different strains, and then you get this gradient here in this function, and you get the total result. And with that, Sosky was able, this is the last figure I want to show here, Sosky was able to measure the apparent modulus of a low-density polyethylene and a polystyrene as a function of time at different strains. This is the strain at the outer edge, gamma R here. This is the strain, small strain, large strain. He uses his correction function, and from that he gets then the ratio of the strain tensor versus the linear, the ratio of the relaxation modulus divided by the linear relaxation modulus, and this is the function which Osaki had been plotted. So with plate-in-plate geometry, the analysis is a little harder, but you're able to produce step strain experiments and analyze them in terms of a relaxation modulus, even at large strains. And that's a very powerful technique. It's probably, in some cases, it's the only technique really to get good step strain data for complicated samples. That's all I want to discuss about rotational rheometers, and also it's all I want to discuss about shear rheometers in general. Next time we will talk about extensional rheometers.